All right, so this video is on quantitative changes in equilibrium systems. So now that we know how equilibrium systems can be affected using Le Chatelier's principle, we know how to calculate KEQ, what we're going to do in this video is actually look at some more data, how to calculate KEQ, and in particular how to calculate reactions that are not at equilibrium and what happens, which way do they proceed, and then go on from there. So, to start off, reactions not at equilibrium. So if we look at this initial reaction, 2NO2 gives you N2O4. I've used this example many times. If we look at the two graphs that I've given you, equilibrium is not reached until your NO2 concentration reaches 0.0125 moles per liter. So I grabbed that number straight off the chart. So that's down here, okay? So around here is, I called it 0.0125. Okay, now you'll notice in the first graph I started with only N2O4 and 0 NO2, and then in the second graph I started off with the opposite, 0 N2O4 and lots of NO2, and in both cases you see that you're at this certain temperature, your equilibrium is going to be reached when your NO2 concentration is at 0.0125 and your N2O4 is, I don't know, at 0.035-ish. So again, and it's just to reiterate, doesn't matter where you start from, at a certain temperature, we're going to hit that chemical equilibrium, and it should be the same in both cases. So now I'm going to introduce you to the reaction quotient, which we call Q. Okay, this is the value obtained by substituting initial concentrations into the equilibrium expression. So we're still going to use that equilibrium expression of KEQ, but instead of plugging in our concentrations at equilibrium, we're going to plug in our concentrations that we start with initially. So for AA plus BB equals CC plus DD, here is your exact same expression that you would get for KEQ, where you have your products on top, on your reactants on your bottom, and your exponents end up being your coefficients from the balanced chemical equation. The only thing that's changed is the numbers that we would plug into here are initial concentrations, not equilibrium concentrations. So that's why we call it Q, not KEQ. Why am I bothering to teach this to you? Basically, what the Q value does is it determines the direction of a reaction. Because sometimes just by looking at the numbers, it's really hard to tell which direction a reaction is going to proceed in. So when Q is greater than K, that means the ratio of products to reactants is too large, and the reaction will proceed in the reverse direction to reach equilibrium. When Q equals K, the system is at equilibrium, and when Q is less than K, it will proceed in the forward direction. So this sort of slide and these notes give you sort of an explanation why. To me, it's a bunch of mumbo jumbo. All you need to know is this next slide. Okay, when you plot the symbols of Q and K, when you calculate them, you actually plot them on a number line. So if this is 0, 1, 2, 3, 4, whatever, a traditional number line, you plot the two values on there. Okay, and the reaction will always move in the direction from Q to K. So let's say in this case K was 0.6 and Q, we calculated it out and we got 3.5. I put my K value and my Q value on my number line exactly in this point, and I draw an arrow from Q to K. I see, look at the arrow that I drew. It looks like I'm favoring reactants, and that's exactly how you figure it out. Okay, so because I've drawn my arrow heading towards the left, that means we're going to favor reactants. So to go from my initial concentrations to my equilibrium concentrations, I have to use the reverse reaction. Let's do a few more examples. Okay, so determining the direction of a reaction. So here is a reaction, 2NO2 and N2O4 in equilibrium. The K value at equilibrium is 0.45, and that's at 135 degrees. Here are a bunch of concentrations, okay? So here are my initial concentrations. So when I start off with all NO2 and no N2O4, obviously, if I have only reactants and no products, my reaction is going to proceed to the right. That's kind of easy. We've been able to determine that on our own, okay? Same thing with experiment number 5 at the bottom. If I start off with no NO2 and all N2O4, I know I've got nowhere to go but in, but in that direction. Okay? So in both of these cases, it's been easy so far for us to predict if it's going to go right or left. The tricky part, and this is why Q comes into play, are the ones kind of in between. So if I look at experiments 2, 3, and 4, I've got various concentrations of NO2 and N2O4 that I'm starting with. So in my second experiment, I start off with 0.3 moles of NO2 and 0.010 moles per liter of N2O4. Just by looking at those numbers, you can't necessarily tell for sure, based on the temperature and those numbers, which way this reaction needs to proceed to reach equilibrium. So that's when we calculate Q. So I've got this value for Q. Where the heck did I get that number from? Here is my Q equation again. So my products are on the top, my reactants are on the bottom, and I basically plug in these two numbers. So I plug in 0.3 on the bottom squared, 0.01 on top, divide the two, and I get 0.11. When I plot that on a number line and I compare it to my K value up here, okay, K ends up being further on the number line than Q, right? So if this is 0 over here, this is 1. Q is over here, K is about here. I go in the direction from Q to K, I make products. My reaction proceeds to the right. So the same thing happens again in experiment number 3 and 4 over here. I take those numbers, I plug it into Q, I calculate a value, and then I plot Q and K on a number line, and I figure out what direction the reaction's proceeding in. So that's your basic way of determining the direction of a reaction. Okay. So again, here are all my values of Q and K on the number line from the previous slide. So whenever I draw an arrow from Q towards K, whichever direction my arrow is drawn in, that tells me what direction the reaction proceeds in. All right, let's go through an actual example with some real calculations instead of me just giving you a pile of numbers. So, calculate Q to determine the direction of a reaction when the concentrations starting off are as follows. So I'll let you read through those numbers. And I've given you the equilibrium constant for the reaction at 5.67. So I give you initial concentrations and a value for KEQ. So your answer in this case, I think, oh yeah, sorry, I have to write them all in. You have to calculate Q. So your expression for Q, again, is going to be your products over your reactants. So in this case, it's your concentration of CO times your concentration of H2 to the power of 3 all over CH4 and H2O. So now I just plug in my numbers from the initial concentrations in the question. So in this case, I've got 0.5, 0.8 cubed, all over 0.1, and 0.2. If you're doing this at home, you should be punching these numbers into a calculator along with me. So when you do that, you get an answer of 12.8, and that's your value of Q. So let's plot these values on a number line. So here's 0, here's say 15, okay? So my value for K is about here at 5.67. I gave that to you in the question. My value for Q is 12.8, all the way over here. Draw an arrow in the direction from from Q to K, tells you that the reaction is going to proceed to the left, or we're going to make reactants. So that's basically how to determine the direction of a reaction. You have to calculate Q and compare that answer to your value of K. All right, let's do another example. Again, you should be able to do this on your own at this point. It's pretty much exactly the same as the first example. So if you want to stop the video, try it out, and then start it up again, I'm going to take up the answer. So if we go through the answer now, the following concentrations of gases are present in this container. So those are my initial concentrations. So those are going to be my value for Q. So again, we do products over reactants. So I do NH3 squared over N2 and H2 cubed. And I punch in my numbers straight from the question. So in this case, I get 0.2 squared divided by 0.1 and 0.3 cubed. If I do that and punch that into your calculator, hopefully you've already done that, you get 14.8. That's your value for Q. So now, again, and don't be lazy, actually draw out a number line. It helps so much. Here's 0 on the number line. What's my highest? 15 again, say. So I've got a K value of 0.4. Whew, that's really close to 0. And I've got a Q value all the way over here of 14.8. Draw an arrow from Q to K. The reaction, again, just like the last example, proceeds to the left. So in this case, I'm basically going to make more N2 and H2 in order for the reaction to hit equilibrium. Okay, we're going to do one last example in the video, and I don't want this video to be too long, so we're actually going to stop there and do the last couple of examples in class. So this one's a little bit more tricky, but we're going to be able to still go through our knowledge and apply that to this. So let's read through together. Carbon monoxide reacts with water vapor to produce carbon dioxide and hydrogen. At 900 degrees, K is 4.2. Calculate the concentrations of all entities at equilibrium. 4 moles of each entity are placed in a 1-liter closed container. So step 1 says calculate the concentrations given. So in this case, I'm using 4 moles of each entity, and they're placed in a 1-liter container. So it's 4 moles per liter, or 4 molar for each one of them. Okay, so all my concentrations in this case are equal. So this makes it tough, because if I were to set up an ice chart right now, you're basically going to see that all of my concentrations are equal. So there's no way of me actually looking at this and knowing which way the reaction's got to proceed. So again, sometimes it's obvious. In this case, it's not obvious. So we have to calculate Q to figure out what reaction or what direction the reaction will proceed in. So let's do that next. So to calculate the value of Q, there's your answer. So I put products over reactants, and it's 4 times 4 divided by 4 times 4, which ends up being 1. So your actual calculation in this case is pretty simple. So now when I compare that to K, so again, if I draw my number line, and I've got 0 over here and say 5 over here, okay, I'm going to put Q here, and I'm going to put K over here because it's 4, right? 4.2. Now if I draw my arrow in the direction from Q to K, I can see that my reaction proceeds to the right. So I'm going to make more products to reach equilibrium. That's going to help me when I set up my ice chart. So now I have to calculate the concentrations at equilibrium. I gave you the initial concentrations. Now we have to calculate the final concentrations. So my next step, now that I know I'm going to make more products, I got to set up, so since Q is less than K, reaction's not at equilibrium, and we proceed to the right. So we're going to make products. So when I now do my ice chart, I've got my initial concentrations in 4 all across the board. Since I know I'm going to make products, when I do my change in concentration, I know my products. So CO2 is going to go up by X. H2 is going to go up by X, again, because I know the reaction proceeds to the right and makes more products. If I'm making more products, that means my reactants are getting used up, so these are going to go down. So you guys have to understand that if I had not calculated my Q value, I would not know if my reactants went up or down, and if my products went up or down. So that was a really important step to do before I set up my ice chart. So now my equilibrium concentrations for my reactants is going to be 4 minus X, and for my products is going to be 4 plus X. So now we just have to solve for X. How do we do that? Well, now we're not looking at Q anymore. We're looking at KEQ because we're at equilibrium. So KEQ is products over reactants. So we have 4 plus X times 4 plus X divided by 4 minus X and 4 minus X. Okay, another way of writing that in this case, just to make it a little bit simpler for you, 4 plus X squared divided by 4 minus x squared. And I gave you the value of KEQ in this question. I gave you 4.2. So basically you can see there are going to be some cases, and we're going to do more of these in class, but there are going to be some cases where you actually end up with a quadratic equation, and you need to use the quadratic formula to solve it, okay? You will see those, and like I said, we're going to go through some examples of that in class. This one starts off as a quadratic, but if you remember some skills from math, you can do the same thing to both sides and keep everything equal. So I can start off by taking the square root of both sides, and what that does is it gets rid of these two squares. So if I have the square root of 4.2, that equals 4 plus x divided by 4 minus x. Then I cross multiply, and it's a lot easier to solve for x. I'm not going to take you through all the mathematical steps here because this is chemistry class, not math class. But basically, you can times the square root of 4.2 times 4 minus x, and then rearrange and solve for x, okay? So when you solve for x, x can actually be two numbers, 1.39 or 11.61. When you get two answers for x, there's always going to be one that's impossible. And in this case, hopefully you can see, x has to go up here, right? So if I start off with 4 moles, can I take away 11.61 moles? Not possible. Okay, I only started off with 4, so I can only take away a maximum of 4. So this is my answer that actually is not possible. So I can cross that one out. Because it's too big, if I did 4 minus 11.61, I end up with a negative concentration, which is impossible. But 1.39 works really well. So that's the one I'm going to use. So if I go through step 5, now I can actually calculate the equilibrium concentrations. So for my reactants, I have carbon monoxide and water. So I'll just write those in. CO2. So my concentration of CO2 and my concentration of H2O is basically 4 minus x, which is 4 minus 1.39, which equals 2.61. My products are CO and H2, and in this case it's going to be 4 plus x, which is 4 plus 1.39, or 5.39. So those are my final concentrations of my reactants and products. Question done. So I'm going to show you one more slide, and then we're going to go through the rest of the notes in class. Oh, sorry, I don't have that slide. So, okay, yes, so we'll go through this one. So, calculations with imperfect squares. A couple of things that I want you to look at. There's something called the 100 rule, and it's an assumption made to simplify some of these problems. So, and this is really important. So, if you want to put a star beside this or highlight it, okay, if the ratio of the initial concentration of a reactant divided by K is greater than 100, then X ends up being very small compared to your initial concentrations and may be discarded from some calculations. We can actually take it out and eliminate the need for a quadratic equation, which I'm sure you guys will be happy with. An example of doing that is this example number 4. I want you guys to try this on your own. It's straight out of your textbook on page 472. So you have the full answer already in your textbook. Read through it, try it. It's the exact same process, except we're instead using this 100 rule. So see if you can read through the textbook and figure it out. And we will take up this entire answer in class. But I'm going to cut the video short here, just so you're not listening to me talk forever. So we will do this example and the last example in your notes. We're going to do those basically as sort of your check your understanding in class. So that's it for today, and if you have any questions, again, we'll make sure to answer those in class.